from lecture week 5 about the energy, you study that work is mathematically represented as the product of F times the linear distance covered, or delta X. And the SI unit for work is Nm, or Newton meter. Also, we know that pressure can be expressed as force divided by area. Before we delve deeper into the Bernoulli equations, let's understand this animation. By understanding the animation, we will better equipped to derive the Bernoulli equations, which is represented by the following formula here, where P plus half rho V square plus rho Gy equal to constant. Imagine two individuals applying force to push a liquid in two separate locations within the pipe. The first person pushed the liquid at the lower end in the direction from left to right, while the second person pushes the liquid from right to left at the upper portion of this pipe. In both scenarios, the displacement caused by the work done at the lower end of the pipe is represented by x1, and the displacement at the upper end is denoted by x2. First, let's see the event where the first person pushes the liquid at the lower end from the direction of left to right. The work W done on the lower end of the fluid by this person is equal to W1 equal to F1 delta X1. From the pressure equations, where P equal to F over A, we can rewrite the work equation as W1 equal to P1 A1 delta X1. Since the equation for volume can be represented as area times length, then we can simplify further the work done on the lower end of the fluid by the fluid behind it into W1 equal to P1 V1. Here, V is the volume of the lower blue region of the animation. Similarly, the above step can be reproduced for the work done on the top position of the pipe, but it should be noted that the force on the fluid at the top is having opposite displacement. Therefore, we can say that W2 equal to P2 V2. By the equations of continuity, the volume of fluid that passes through the blue region at the bottom end in the time of delta T should equal the volume that passes through the blue region at the top of the pipe during the same time interval. Therefore, the net work done by these two forces in the time delta T is equal to W fluid equal to P1V minus P2V. The work done on the fluid can be used to change both the kinetic energy and the gravitational potential energy of the fluid. For example, if the fluid is moving through a pipe, the work done on the fluid can increase its speed and can also move the fluid into a higher or lower positions, thus changing its gravitational potential energy. Because of this, the net work done by these forces during the time interval T is the summation of the kinetic energy and potential energy. The change in kinetic energy of the fluid is given by the equations of delta kinetic energy equal to half mv square subscript 2 minus half mv square subscript 1, where m is the mass of the fluid and v2 subscript 2 are the liquid velocity at the lower end of the pipe, and v2 subscript 1 is the liquid velocity at the top end of the pipe. The change in gravitational potential energy of the fluid is given by the equations of delta PE, or potential energy, equal to mgy2 minus mgy1, where m is the mass of the fluid, g is the acceleration due to gravity, and y1 and y2 are the initial and final height of the fluid. The net work done by the fluid on a segment of fluid is given by the equation W fluid equal to delta kinetic energy plus delta potential energy. This equation is a manifestation of the work energy principle, which states that the work done on an object is equal to the change in its kinetic and potential energy. So far, we have been presented with two equations, W fluid equal to P1V minus P2V and W fluid equal to delta KE plus delta PE. Therefore, we can substituting expression for each of the term which give this equation here. We can simplify this relationship further by taking advantage of the formula of rho equal to mass over volume and divide all the term by V, or volume. which will give us these equations here at the bottom. Apart from that, we can further simplify this equation into this form here.